We'll get started with our last session of the day before we get to our reception. So this one is called Space Power Systems. Our moderator is Carol Lane, otherwise known as my boss. She is the president of the American Astronautical Society. She is also president of Synergy, LLC, consulting in the fields of aerospace and energy. And she also works with X Energy, LLC. From 2003 to 2014, she served as Vice President of Washington Operations and Vice President of Civil and Commercial Space for Ball Aerospace and Technologies. With 25 years of defense and space community experience in policy, government relations, and business development, Carol has worked with the federal government and Congress, as well as over 18 years in industry with Lockheed Martin and TRW, Northrop Grumman, both in the operating plants and in the Washington office prior to joining Ball. In 1988, President Reagan appointed Carol to serve as the director of the Office of Commercial Space Transportation under the Secretary of Department of Transportation. So, Carol, over to you. And here's your clicker.
So, I don't know which is more of a challenge with the propulsion panel, which actually was dealing with carb loading, and we're the last panel before drinks. So it's we'll see which one works. As we heard a lot today, there's a discussion of, as a community, we're setting our sights on going farther and to different places that we've been to, both with humans and robotically, and staying longer on various destinations. And a key driver to achieving these goals is the capacity to produce power. As NASA says, abundant power expands the capabilities of every human and robotic mission, including missions to asteroids, planets, moons, libration points, and orbiting structures. Furthermore, abundant power provides benefits for all phases of spaceflight, vehicle operation, including vehicle operations, electric propulsion systems, and destination applications. So space energy is a critical cross-cutting technology, and it is as fundamental to our success in our space endeavors as energy here on Earth is to our life here. So today we're going to talk about where we are in the space power world and how each of the people on the panel, how their areas fit into the overall picture, and then talk a little bit about where we want to be and how we get there. What I'm going to do is introduce each of the panelists all at once now, and then we'll just go down and have the presentations. And again, as you think of questions, please digitally provide them, and then we'll have also some time for questions at the end of the panel. John Hamley is a 1985 graduate of the William Raines School of Engineering at Youngstown State University, another local, and the manager of the Radioisotope Power Systems program at NASA. He has also received a master's degree in electrical engineering and business administration from Cleveland State University in 1990 and 2003. He remains in contact with the Youngstown State STEM College as a member of the Electrical Engineering Department's Industrial Advisory Board. Prior to his management of the RPS program, he was the acting deputy director of spaceflight systems at Glenn. He also held division and branch chief positions in the spaceflight project and space propulsion test facilities operations areas at the center. Before entering the management track, he was the lead electrical engineer for electric propulsion and space plasma work at Glenn. His key contribution in this area included development and flight of power electronics for the N-STAR ion propulsion system, which was primary propulsion for the Deep Space One and Dawn missions, the plasma contractor for the International Space Station, and Hall and ArcJet thrusters. Next on the panel is Tracy Bishop. As the Deputy Assistant Secretary for Nuclear Infrastructure Programs, Tracy is responsible for the management of the Office of Nuclear Energy's infrastructure programs. This includes NE's field operations at the Nuclear Energy Oak Ridge Site office, supporting the lease, administration of uranium enrichment capabilities at Oak Ridge Reservation and the Portsmouth Gaseous Diffusion Plant. In this capacity, Ms. Bishop is responsible for a large portfolio of infrastructure programs spanning facility management, capital asset planning and construction, safeguards and security, emergency planning, and nuclear materials management. These programs and capabilities enable critical nuclear energy research and development activities by providing and maintaining safe, secure, and compliant facilities for multiple customers within and external to the Department of Energy. She is also responsible for delivering compact, safe radioisotope power systems, heater units, and related technologies to support NASA and other agencies in space exploration and national security missions. Ms. Bishop has more than 25 years of experience in facility management, environmental safety, and health oversight experience with the Department of Energy. Before joining NE in 2008, Ms. Bishop served as the acting director of the Office of Facilities Operations, Office of Defense Programs with the National Nuclear Security Administration. Ms. Bishop holds a bachelor's degree in nuclear engineering from Georgia Institute of Technology and a master's in business administration from the University of Maryland. She is certified as a project management professional with the Project Management Institute. Larry Traeger is director of the Advanced Power Systems business at Aerojet Rocketdyne. Previously, he was general manager of Hamilton Sundstrand and Rocketdyne, a division of Hamilton Sundstrand's United Technologies Corporation. He is responsible for the overall leadership of the advanced power system business at Aerojet Rocketdyne. These products include power systems and technology for the International Space Station, multi-mission radioisotope thermoelectric generator, MMRTG, and the enhanced MMRTG, as well as the next-gen RTG and the Orion power system. His team is also responsible for designing and building the electric power system for Sierra Nevada's Dream Chaser. In addition, he is responsible for the Space Electronics Test Facility, which has testing capabilities for thermal vacuum, cycling, and vibration. Prior to his assignment, he was the controller for the HSR business and previously served as manager of financial planning and overhead costs for Pratt & Whitney Rocketdyne. He holds a bachelor's science degree in business administration from Ohio State University and an MBA from Xavier University, and completed a master's in quality management from the National Graduate School. Following his undergraduate education, he served as an officer in the U.S. Army and was awarded the Army Commendation Medal for superior service. So thank you for your service. Oops.
Okay, I found this on the web for you.
Okay. I didn't touch it. It does listen to everything you say. A little scary. And then finally, Greg Semrau. Greg has worked as a systems engineer at Moog Space and Defense Group since October 2011. His primary responsibility is in systems architecture and analysis of new product development ventures. Greg has pioneered the development of the Modular Electric Power System, MEPS, and led the power management systems effort within Moog. He is a senior member of AIAA and is membership chair of the Aerospace Power Systems Technical Committee and chairs the Space Nuclear Power Systems Technical Track for IECEC /IPC. His focus on the next generation technology development, acquisition, and commercialization, and how it dovetails with product development strategy. So what we're going to do is give everybody a chance to go through, with John starting as a general overview of space power, and then we'll go down the line. Okay. Over to you.
Thank you, Carol. So Thank you all for hanging in there for the last session. It's kind of a common thing. I've given many talks at many conferences about power, and usually the last session of the conference. My favorite memory was once it was myself, the session chairman, and the guy in the room who was ready to tear it down when we were done, and he was pleading with me to hurry because he had a date. So hopefully you all will be a little bit more receptive. So talking about the power to explore, can I have the... Yeah, I can't fail at this without even having it. Okay. So we're off to the moon again, and this time to stay. And power is very critical for our ability to explore the moon in a vast variety of ways. And probably the most important is surviving the lunar night, because that's probably one of the biggest challenges to a long-term stay on the moon. So we're going back again. It's very exciting. I was 6 years old the first time we went. I will have another 6 in my age when we go back. I don't know how excited I am about that, but it's good to see that we're going back and going back to stay. Ken did a great job talking about earlier today about the Artemis program and the origins of the name, so I won't spend much time there. Now this chart kind of goes over the architecture. And there's two, I like to break this chart in half. There's two distinct phases to this. The upper half is the Artemis missions, the Orion spacecraft, the Gateway, and the power and propulsion element. Those are very solidly solar-powered vehicles, a very solar-powered architecture. When you get on the bottom half of the chart and you start talking about exploration on the moon and, again, surviving the lunar night, as we start on the on your left there with the early exploration stages where we're going to be sending robotic missions to the moon to look for resources, because part of the reason we're going there is looking for water and other resources. Those will be smaller, lower powered devices, but if we want them to last more than 14 Earth days, they're going to require either very excellent energy storage systems or nuclear power, such as radioisotope power. And these are sub-kilowatt class devices, but as you start to move to the right and bring humans into the picture, you now are starting to talk about tens of kilowatt class power systems. And again, over the 14-day lunar night, what really tends to close the trade space very well is a fission power system of some type. So if you look at the power and propulsion element, again, as I said before, this is very solidly a solar powered system, 50 kilowatts. It's not a small system. There's a lot of power there for electric propulsion. As you heard from my resume, I'm a huge fan of that. Been around it for a while, and it's a very, very excellent way to provide a gateway power and also provide maneuverability for the systems as we go on and explore the moon again. If we look at the lunar technologies, and again, as you start to have your sustained presence there, you start to do things like in situ resource utilization, or even and have small devices. There's a wide spectrum of power requirements for each of those devices. Some of them are sub-kilowatt, in which case, again, I would bring up the feasibility of a radioisotope power system for those devices. And as you start to look at in situ resource utilization, where you're cracking water potentially to make fuel, or trying to process water out of the regolith for habitation, those are tens of kilowatts, and again, the habitations themselves will require extensive power. So there's a number of options available here. Radioisotope power systems, the photo there is from the Apollo days. That is a RTG there in the middle of the picture with an astronaut standing near it. The nice thing about RTGs is that the radiation coming from them are mainly alpha particles and a few neutrons. The alpha particles never make it out of the device, but there is a slight neutron flux, but they're very well suited for situations where they could be near humans or elsewhere, even in the field, for the ability to power remote sensors such as seismometers or whatever it is that you're looking for. But again, as we start to look at habitation, in situ resource, I keep bringing this up, fission power systems are really well suited for that. And the agency is currently working on both of these systems. My program, in the RPS program, is working on both static and dynamic power conversion systems to facilitate these type of instruments. And also, by the way, someone was talking earlier about life testing and wanting to do a lot of space-based testing. We think the moon is an excellent place to do a demonstration mission for a dynamic power system because the trip time is very short and the mission time could be a year or two or more, but nevertheless, it will give us a lot of good data there. In terms of fission, excuse me, I keep saying fishing, I'm a fan. Sorry about that. Fission power systems, again, the Glenn Research Center is working on those as well with the kilopower and the crusty experiments that were done earlier, giving us a very good basis from which to start to look at these architectures and how we can provide tens of kilowatts of power. And demonstration missions are being planned right now, and we're looking forward to the results there. Once you get beyond the moon and you start talking about the robotic exploration, and I have the solar system, and very specifically I have in more there because people are talking about things like interstellar probes and other things. The targets that the Science Mission Directorate gets, where we decide where it is that we would like to explore comes from a thing called a decadal survey. Obviously, by its name, it comes out about once every 10 years. And that's a gathering of the science community telling us what they're interested in and where they think our investment should be in terms of missions. And the latest survey identified the locations that you see there, and I have an asterisk by each one of those, which requires either what I will call a novel or a nuclear power system in order to effectively explore in those areas. There is a place for advanced solar and battery power in planetary systems. I have pictures here from the Juno mission and some of the really cool photographs that come back from that. I think that those are really, I don't know what the science is. I won't begin to tell you that. I just know that they really are some spectacular images. The interesting thing about Juno, it is a solar-powered mission, which opens up the possibility of doing solar power at Mars. However, those solar arrays are north of 10 kilowatts in near Earth orbit. However, when you get out to Jupiter, they're producing a few hundred watts because of the fall off of solar radiation. And also, the other reason that they work is that they've done some very interesting orbital mechanics to keep that spacecraft very short times, to keep the times that it's in the radiation belts of Jupiter very short, because every time it transits through there, those solar cells are degraded by that radiation. Now that can be done, you can do things with shielding and so forth to slow that process down, but nevertheless, it's a very interesting situation where solar power can be made to work at Jupiter. However, there are limitations. In terms of surface exploration, radioisotope power systems right now, we have one exploring Mars right now on the Curiosity rover. We've got the Mars 2020 mission to launch in July of next year, July or August. But nevertheless, this is an interesting application of nuclear power where we will trickle charge a battery, and then once the battery is topped off where it needs to be, then we're able to maneuver the rover and do some really cool exploration. And if you've seen some of the results that have come back from Mars, including, I think the latest result is they're finding high concentrations of methane on Mars, which is new science for us. But that's all enabled by radioisotope power. Radioisotope power is also very obviously good for deep space. I've got some photos here from the New Horizons spacecraft, the Pluto system, and also Ultima Thule, which is a Kuiper Belt object. In this case, the power system was a GPHS RTG. This was a product of the Cassini, Ulysses, and Galileo era. We don't have many of those left. In fact, right now we have no flight units of that left, and the RPS program is working to recapture or redo the capability of a higher power 300 to 500 watt radioisotope generator to enable missions such as this as we move on. Uh-oh, I broke it. I'm pushing the button. Oh, there we go. Hold on. All right. Thank you. So I have here radioisotope power for aerial exploration. This is really cool. Last week we announced, or early this week, we announced that A mission called Dragonfly is a go in New Frontiers 4, very similarly powered as the Mars Curiosity rover with a single MMRTG, but nevertheless this is now going to be flown to Titan, one of Saturn's moons, and then we're going to explore Titan by flying around with effectively a drone. So we'll go from point A to point B in the air or in the atmosphere, which is really, to me, this is really cool. And one of the best parts of my job, I get to be involved with some really interesting missions. But again, without nuclear power, this mission does not work. And we've done the easy targets, and now we're off looking at other things. Now, fission power also has its place in science exploration when we're looking for missions that close with or require tens of kilowatts of power, where we can take some of that power and then use nuclear electric propulsion to cut back on trip times. And then once we are on site, we can then also use that power for higher power communications, increasing bandwidth, or with more elaborate instrumentation suites than is typical that we could do with a few hundred watts of radioisotope power. It is not a replacement by any means for radioisotope power. However, it's an additional capability. And also when we start to talk about exploring some of the icy moons and wanting to work our way through the ice down to the underlying oceans, fission power also could be a good fit there. So as we move on, again, we're starting to try and look at more elaborate missions, looking at icy worlds, going to explore Europa, Enceladus, Uranus, and then also we've heard talk of interstellar probe. Nuclear power has its place and will enable these missions, and we'll continue to strive to improve efficiencies and make these systems very well suited for these applications. So that's all I have. Thank you.
Thank you. Tracy?
Good afternoon. On behalf of the department, thank you for inviting us to participate today. Our organization is generally focused on commercial nuclear and providing the capability to support research and development to help enable the organizations that support the commercial nuclear power plants maintain that power generation capability. There's a lot of unique synergies that support NASA in the efforts to enable nuclear power, and that's really how we see ourselves, as a partnership with NASA to enable their missions. So how do I do this? This one? Mm-hmm. Okay. So nuclear technologies, the department has a very long history of designing, developing, and deploying nuclear power systems to support space exploration. Primarily falls into two categories: radioisotope power systems, that spans from radioisotope heater units, which are very small, 2-gram little pellets that keep instrumentation warm, to more complex radioisotope thermoelectric generators. And then also fission power systems that includes nuclear thermal propulsion and surface fission power. Recently, in 2016, the department and NASA updated their Memorandum of Understanding. It was an old document from 1991, looking forward to improve our partnership and how we operate together to leverage both of our capabilities to support these missions. And that document really provides a framework so that NASA has access to DOE capabilities and the expertise that's resident at our national labs. So just briefly with the radioisotope power systems, as you've heard many times today already, they provide electrical power. The picture to the right is a plutonium-238 pellet. That is our material of choice, and that is an unclad pellet, so you can see it does generate a lot of heat. It does convert the heat from a radioisotope into electricity, and we have spent a lot of effort over the last decade to reconstitute the domestic capability to produce plutonium-238. And as of date, we have already had several campaigns. We've made over 350 grams, and some of that material has actually made it onto the Mars 2020 RPS that will be going into space. That just proves the complete supply chain. Next one. So constant rate production, one of the areas that NASA and DOE have really collaborated on over the last few years is looking at how we maintain the capability. Previously, the capability was always put in standby between missions, because those missions were between 7 and 10 years apart. That was very expensive from a infrastructure standpoint to stand up capabilities, hire people, train, get systems and equipment certified, run the process, and then stand down. So in working together with NASA, we came up with a strategy to maintain a steady state production rate that is defined by two main areas: producing heat source plutonium oxide and producing fuel clads. And that is a huge benefit to NASA and a huge risk reduction. So it ensures that there's a fuel supply that's available on the shelf, ready to go for mission use. And the estimates are that it's going to reduce the life cycle between missions by 2 years, and with a 25% reduction in cost for the delivery of an RPS system for missions. We've also gone through and done a very, very detailed look at our inventories and really looked very hard at how we can support, and we've worked very closely looking at future missions, and we do have sufficient inventories of plutonium to support NASA's needs through the 2030s, including the Mars 2020 mission and then the new Dragonfly mission that was just announced. So fission power is another area where we're starting to work more closely with NASA, and you heard Jim talk about that earlier today, and John, in two major areas: nuclear thermal propulsion, which is supporting design and development of a low-enriched uranium system by the mid-2020s, and then also looking at surface fission power to have a sustainable power presence to support either lunar or Mars surface habitats through the mid-2020s. And so how do we do this? So there's a lot of capabilities that the department has invested in at our national laboratories over the last decade that is really focused on materials and fuels research capabilities. Those capabilities include irradiation capabilities, post-irradiation examination, making sure there's adequate supplies of nuclear materials and fuels, and also doing modeling and simulation. These capabilities are very key to the commercial nuclear industry. There's a lot of ability and interest in having synergy with other government agencies, and it puts together a nice environment to bring all that collaboration together with universities as well as commercial industry and government to work together to leverage all of these challenges that we have. And the two pictures there, the first one is the Advanced Test Reactor that's at Idaho National Laboratory. That is actually going to be producing plutonium-238 in the near future. That's one of two reactors. We also have the high flux isotope reactor in Oak Ridge, Tennessee, that's already currently slated to produce 238. But the ATR is also one of our main test reactors. And underneath is the transient reactor test facility, also at Idaho. This reactor was in cold standby since 1991. We recently brought that up in 2016 to support transient testing and taking fuel to extreme environments and being able to understand how it performs. So business processes are another thing that's really key, and some folks brought that up earlier today. Making sure that the regulatory environment for nuclear is always very challenging, but we've been working to make sure that there's sufficient transparency in there so that we can have successful collaborations. And things that usually come up are intellectual property rights, licensing of technology, and launch approval authorities. These are all areas that recognize that we're trying to work together to reduce those barriers to market, to enable to promote the industry going forward. And as I already mentioned earlier, we do have this Memorandum of Understanding, and as part of that Memorandum of Understanding, it's really opening up the department's contracting mechanisms that we have with our national laboratories to open up those doors to let government, let industry come in and direct partner with the lab, have access to those limited infrastructure capabilities so that they can work together. The government has invested over $1 billion in Idaho alone over the last decade to make sure that these research capabilities are up and available. And one thing we really do promote, we have a lot of mechanisms in place to have industry opportunity announcements, partnerships with universities to have this nuclear research, and also build the pipeline of students. So in summary, there's been a lot of recent successes. There's lots of opportunity going forward, I think, in order to move this technology, get the innovation put into the system going forward. And some of our other bigger efforts that are going on in the commercial industry that you all may have heard about, small modular reactors or microreactors. Microreactors are actually reactors that can be transported into remote locations and be available for remote communities or other uses. Looking at kind of that next step, going forward to driving that innovation. And then also, investing in the technical expertise. I think that's really key, as we've heard from the aerospace industry as well as the nuclear industry. That's just key to make sure that there's enough people and students in the pipeline going forward. Thank you.
Good afternoon. Thanks for your attendance. Having trouble reaching the screen. There. Okay, these are the products, recent products as well as current products in our portfolio for the Advanced Power Systems business unit. The space station obviously has been flying for a while, but go back. I don't know why it run back. How'd you get it back? There you go. So the space station, you've got 8 solar array wings on the space station. Each one controls a power channel, and those wings, by the way, are about 100 meters long, so they're pretty big. The bottom left corner is the MMRTG. That's the multi-mission radioisotope thermoelectric generator we've talked about. It is multi-mission in that it works in the vacuums of space or on the surface of a planet. And as John and Tracy had indicated, it's powering the rover up on Mars. The next picture in is the batteries, the lithium-ion batteries. We've built those. They're being deployed on the space station to replace the nickel hydrogen batteries. And then the Dream Chaser vehicle is we are providing the electrical power system for the Dream Chaser. It's about a 6 kilowatt power level, and we'll talk a little more detail about each of those. The last one is just the transfer vehicle associated with the Gateway project. So the Gateway is undergoing Project Artemis, as Ken talked about this morning, is vital importance for our country and for NASA to go to the moon and to back to the moon and to Mars. Okay, the International Space Station. So truly international. You've got Japanese agency, Canadian agency, ESA, and we've got NASA, and we've got the Russian Space Agency. The first hardware was delivered to the station in 1998 by the Russians, and since 2000, the U.S. has had astronauts on the space station, so it's actually been operational for almost 19 years. We've had for the last 10 years full power and uninterrupted power, I might add. The design that we utilize focused on 100 kilowatt power level, so it's the highest power source of anything flying in space today. If you compare that to the Gateway project, which I believe is targeting about 70 kilowatts. The space station has been a real marvel, and to get all that to work has really been amazing. It's targeted, as you well have heard, to 2030 and maybe even beyond that. Okay, this is just a pictorial of what I just described. Each solar array wing controls a power channel. There's 8 of them. So you've got the solar arrays on the left side. Down below that, you've got a shunt unit. So the solar arrays collect a lot more power than is needed, so you have to shunt that power. You've got a series of power distribution units that are needed to control each channel. You've got the batteries. So the batteries we built, each battery will replace two of the nickel hydrogen batteries. So there's 48 batteries on the space station. We built 27 ORUs, 24 flight units, and 3 spares. Man, it's hard to get that thing to work. There we go. Okay, so these are some of the hardware, not to bore you with the details, but when we integrated the space station, we worked with many primes at that time, including Loral, who built the batteries. The original batteries were built by Space Systems Loral. The shunt unit was built by Loral. The solar arrays were built by Lockheed Martin. And then all those products to the right there were products that Aerojet Rocketdyne designed and built. The primary power for the station is 160 volts, and you've got to drop down to 120 volts. So 160 for the European needs and 120 for the US needs. So that's what that DC to DC converter does. You've got the remote power control module, which is used to, it's basically a circuit breaker. You've got to have thermal. There's a lot of power and heat and electronics that you have to dissipate. So those are critical things that are required. Okay, the batteries. So we completed the battery contract a few years ago. We built, as I said, 27 ORUs, 24 flight units, 3 spares. The batteries are 15.4 kilowatt hour each battery. Each battery contains 30 cells. They're GSU WASA cells. They're 134 amp hour cells. They're large format cells. So unlike a lot of the cells today, a lot of battery technology is a smaller pin-light cells, the Panasonic 1650, those cells. But these are large format cells that we use. And so far, everything's worked out pretty well. We've got, the battery weighs about 430 pounds, and it was designed for a 10-year life. You can see the different delivery schedule. The first batteries were delivered in January 2017. And like I said, each battery replaces 2 nickel hydrogen batteries, and then we had more delivered, 6 more. We've delivered, all the batteries have been delivered, but 11 have been replaced on the space station so far. You've got 6 more at the end of this year and 6 more in January. There was a battery issue this year, and it had to do with a fuse that malfunctioned on the battery. And so we got a few calls, you know, what's going on with your battery? Well, it was really driven by the battery charge discharge unit. So a lot of the hardware we designed for the space station and built is way beyond its useful life. And so things are starting to break down. We did build a number of spares, but that's the issue with going to 2030 to replace hardware as it's needed. Okay, the Dream Chasers. So our contract with Sierra Nevada for the commercial resupply services 2 is to deliver an electrical power system. So that power system includes energy storage, it includes power management, power conversion. So the Dream Chaser has to dock to the space station, and so you need to convert power from the station to the Dream Chaser. I won't go into a lot of detail, but the power electronics that we're building include high voltage batteries as well as low voltage batteries. We're working with Zen Technology on a lot of the hardware for this vehicle. We're working with ABSL for the batteries. And the HV, high voltage batteries and power distribution, is only used for the descent of the vehicle to control the landing gear and things like that. The primary power comes from the low voltage box, which is quite complicated. I want to add another thing. If you've seen the space shuttle and you've seen this vehicle, it looks like from far, it looks like resembles the shuttle, but just the size of it compared to the Dream Chaser. The Dream Chaser is only like 35, 36 feet long, and I believe the upload mass on that is close to 5,000 kilograms. So the issue is, how do you get, we're building 53 orbital replacement units, batteries, and power boxes. How do you get all that in the nose of that vehicle? Is very, very difficult. And so that's caused some design issues trying to fit. We've had to change the battery from a rectangular battery to a hexagonal battery and so forth. Okay, the multi-mission, John and Tracy have talked about the multi-mission radioisotope generator. We built 3 flight units. Flight Unit 1 was delivered in August. Well, it was delivered a long time ago for fueling to Idaho, but the actual landing on Mars was August 12th of 2012. So it's been almost 7 Earth years. It's operated pretty much without flaw. I think there's been a couple minor issues that we've seen and why there may be a drop in the power, but trying to figure out why, and we've looked at that. But overall, it's been a very reliable power source. This is a TRL-9, obviously, and it's the only thing at that level flying in space for radioisotope generators. So we're also involved with as a system integrator for the enhanced RTG. So taking this technology and evolving it to the next phase, the enhanced version of this basically is taking the same architecture and swapping out the thermoelectric couples. This has 768 thermoelectric couples. As Tracy has indicated, it takes a heat source of plutonium-238, converts it to electricity, and generates about 100 watts of power. Beginning of life is maybe 115 watts, but the end of life is targeting for much less than that. The newer technology is to improve the efficiency. The efficiency on this is only about 5%. The efficiency on the enhanced version is about 7%. The next generation, we talked a little bit about the next generation. The next generation RTG, we're involved with that, or at least we bid on it. So that will generate up to 500 watts of power. It will be modular, which is great. So it'll be the first modular RTG built. So you could go up to 16 general heat source modules, or you could use much less than that, depending upon the mission. So that's the advantage of that. By the way, the F2, as was stated, is earmarked for the 2020 mission. F3, with the announcement of Dragonfly, is targeted for the Dragonfly. Okay, space fission power. We talked a little bit about that. The picture on the left side is the SNAP-10A reactor. Somewhere in one of our warehouses, I have a SNAP-10 reactor, which I've had a couple folks in Albuquerque approach me about putting it in their museum. It's the only nuclear reactor ever to be launched in space by a U.S. company. So that's kind of sad if you think about it, because that was back in 1965. But I think you're going to see more and more as we get into more deep space exploration. You're going to see more nuclear activity, more fission type activities. You know, if we go to Mars, as John pointed out, you could use solar arrays, and they will come into play. I think all these sources of power will be utilized, but fission power is really a good choice for Mars. Maybe not so much for Moon in 2024, unless you end up in a crater, which I'm not sure we're going to get there. But in 2024, just to go to the Moon, you probably could rely on solar for power. But ultimately, you will need fission surface power. And then NTP, obviously, with the desire to get to the deep parts of space quickly, nuclear thermal is a viable option to go along with chemical propulsion. So we're involved with that also. Okay, so I think this is my last chart. But with these contracts, a lot of the contracts we've been talking about here, they don't come every year. And they're onesie, twosie types of things. You know, we built 3 RTGs, 27 batteries, and they come, you know, there's a lot of time in between. So we've had to go out and talk to terrestrial opportunities, including the Navy and so forth, the Army, the Air Force. And one of the things that we did is we entered into a contract with the Navy a few years ago to build an underwater charging station for the UUVs. And that was demoed in the San Clemente, San Diego area last year. It was quite successful. The other is I'm working currently with a battery company that builds nickel zinc batteries, and we actually are building the battery management system for that. So all in all, we've had to go out and talk to different terrestrial type companies. So I think that's it. So I appreciate your participation. Thank you. This is
So my name is Greg Semrau. I'm from Moog Space and Defense. I guess I get the last crack at embarrassing myself with the switch, so let's give it a shot. So when I was invited to speak on the panel, I was trying to think of a good way to architect the conversation. So different from a lot of the other people in the room, Moog Space is a tier 1 supplier. Typically, people may have heard of us as hydraulic controls. We do propulsion. Recently, and I say that past 3 decades, we've gotten to electric motor control, which got us into the conversion game, and then recently we acquired some avionics capabilities. But really, that's pushed us into this realm. And what do we see? So we, kind of exploring the industry, we found electric propulsion is a very driving force. And one of the interesting things is you take a look at like more new space or LEO-oriented spacecraft, and they have a lot smaller needs. They have 500 watts, 600 watts, less than a kilowatt. And then you have some of the deep space exploration needs where they're really starting to drive towards 50 kilowatts. I've seen 150 kilowatts. So how do you balance that? And that starts to drive at the idea of modularity. Nuclear power is starting to make a resurgence. There's been a lot of discussion already on this panel about plutonium-238. And one of the interesting things about that type of system is what kind of output do you get? How do you balance that? How do you work with it? And then, as everybody has heard again and again since late March, so we're going back to the moon in 24. So what is the speed up of development cycles going to do to what you can really develop for new vehicles, where you can actually make your innovations? So some of the mega trends are really higher power, higher efficiency, and where you're going to make modularity. So what we see from our particular point of view is innovating at the interface. So we have some new entrant ideas into the power systems market, but really it's where you're going to try and leverage existing material that people have developed, where you're going to actually try and make a change, and how is that going to be received by the general market to make a more efficient vehicle. So some of those key issues is how are you going to handle that higher power? Is that going to make you drive towards higher voltage so that you don't have a copper mine floating around in space? So dealing with some of these different things starts to drive towards what you're going to do with mass efficiency. So people have started to use the how many kilowatts per kilogram can you get. Typically, people are at about the half a kilowatt per kilogram. Maybe you're starting to push towards 1 kilowatt per kilogram. Could you make it that leap to 5 kilowatts per kilogram? So it's starting to identify what those main pressure points are for the industry and trying to work with it. Also, one of the other restrictions for real modularity is EEE parts capability, and what voltage levels and what current levels that those different parts can handle is really one of the biggest sticking points to endless modularity. But kind of driving back to some of the work that Moog has done in the past, really starting to innovate from a commercial geo standpoint by having a common backplane to plug in different avionics from C and DH, EPS, payload processing, but really seeing this as the leverage point to try and drive some new ideas. Really, it's starting to take and leverage the idea that NASA has put out for the AMP standard, which is how do you create modular circuit cards so that in future state for deep space exploration, you can have a fully populated vehicle and then a bag of parts that you can essentially hot swap in space. So starting to take and say, all right, NASA has come out with a platform and a standard that says this is where we want to go. So it's figuring out how to shoehorn different ideas into this key piece of technology in the standard. So some of the things that Moog has recently been working on, we affectionately call this the Auto-Resonant converter, or the ARC. It's one of the better nicknames for a power converter. But really, in the end, it's a very high efficiency DC-DC converter. So we are planning on being back down in Cleveland in about 6 weeks or so. But in the end, we've shown testing that it's about 97% efficient, starting to creep on 98% efficient power conversion. So as soon as you start talking about 150 kilowatts in space, having 98% efficient conversion really starts to enable you to not have refrigerator-sized thermal converters hanging off the side. So it's some of this enabling technology also allows you to continue using pieces of technology that people have developed and have been high TRL in the past. So you can start to imagine you could go towards 300 volts solar panels. You could go 600 volt solar panels. You decrease the complexity of the SATA. You have some of these different and newer pieces of technology that are able to down convert it to the main bus line that current providers are developing today. And then you don't have to go through and fully develop a new vehicle. You have new pieces of technology that you can insert at key places at the interfaces that really start to drive home new value. So it was mentioned earlier, MEPS, I'll throw this in the category of don't let your boss nickname your project. But in the end, the whole idea is you can start to decouple the power system total requirement into a power need and an energy need. So the whole idea is you can start to enable a lot more flexibility on the energy side. So a lot of people up here have spent a lot of time developing nuclear-based power systems. They deliver a very constant output power. So the idea with MEPS is you can use ultracapacitors to supplement a lot of the high-frequency needs. If you happen to have any sort of inertial actuation, different applications like that, but it also turns into a buffer. Another application is you can put it on the opposite side of a load relay and use that as your inrush current limiter. So you don't have to redesign all of the science tools that you're developing to make it work with a 100-watt output nuclear power source. You can start to have these separate systems that allow you to put 2 kilowatts out on one of the outputs of the power system. So real quick, we've actually taken, people may have heard me talk about this in the past, we've had the idea probably about 6 years ago, and we've actually taken it to flight. So odd anecdote, I had someone tell me back when I first came out with this that it takes 7 years to go from idea to actually flying it. And I, in naivete, laughed, and I'm like, ha, I could do it faster. I beat them by 1 month. I'll take it. So in the end, it's actually coming out with some of the, harnessing a lot of what Dr. Kennedy talked about, figuring out what some of the pressure points are and quickly innovating on it. So we essentially spawned off a separate group that's able to do quick, flexible designs, and we're able to take this from contract award to delivery in about 11 months. So it's really starting to hit on that type of cadence, that 2-year cadence. What are you going to do? What's next? How can you innovate, and how can you be flexible? And really, the low-cost LEO space market is a fantastic opportunity to pilot some of these ideas and really start to drive them towards deep space architectures. Because we'll stumble, we'll figure something out, and then Gen 3 and 5 and 8 is when it can actually be picked up and used from the larger community. I mean, and just to make all the EEs in the room laugh, the thing is about the size of one of those projectors and is 533 farads. So maybe not too many EEs.
A chuckle.
Thank you. It's lonely down here. So I guess really just in closing, to try and drive home the point, schedules force choices. And in the end, you can't redevelop a brand new system every time you have a new idea. We can't say, here's Gateway, fantastic, now tear it up, we're gonna design something completely new for a transport vehicle. So you have to figure out where you're gonna make choices to insert new technologies. What are you gonna do that's actually gonna allow you to do that next leap? And it's really starting to identify what those driving needs are. So from my perspective, it's really modularity and how you start to effectively use it. So I can come up with something if there's a 50 kilowatt delivery need or a conversion need or blah. I can have a 1 kilowatt system, I can have a 50 kilowatt system, but what defines that need so that we can have an effective conversation so that we can say this is good for today, but also good for tomorrow, and then what comes after tomorrow. And then because I'm constantly jealous of, well, that didn't come through all that well, but I'm always jealous of NASA's fantastic graphics that show the fun things that they're doing. Is essentially a picture that shows that Moog has had content that's gone to every planet in the solar system. So, fun. Thank you.
Thank you all. I think we have a couple questions. I did want to kind of start off with probing a little bit more into both the government industry roles and relationships and how they may be evolving and potentially evolving in the future. So let me start off by asking, so with NASA and DOE, how do you in the acquisition process go about working together in terms of acquiring new systems?
As I mentioned earlier, we have some very unique contracting mechanisms with our national laboratories. And so one of the things we're working with NASA on is to develop those partnerships within the government so that NASA has access to our contracting capabilities. And that gives them a lot more flexibility. It also gets them right in touch with those companies and the subcontractors, which a lot of you are in the room are those subcontractors, to be able to work and partner together and really kind of promote the ability and just not reinvent the wheel.
Yeah, what I didn't talk about is part of my overview, and I do want to emphasize the DOE is an amazing partner for NASA, and Tracy's done an awful lot to streamline the process for acquiring RTGs, and I think the partnership between DOE and NASA is extremely strong, and DOE has to hold the contracts for these devices because they use special nuclear material. And an interesting thing that I learned early on when I took over the program was that NASA never takes title to the generator. That remains DOE property. So with some of the statutory requirements and so forth, DOE has to maintain possession. However, one of the things that's evolved, and this has been really, really great, is the two agencies are really playing to their strengths, where Tracy and the DOE are working very hard on fuel production and production of the RTGs, and NASA is managing the technologies that are going into the energy conversion part. And that's a change that's happened over the last several years. So it's been very beneficial to both agencies, and the DOE's been a great partner.
So just to hit on the industry side for a second, Larry and Greg, you both deal with some large government programs as well as working with some of the new, more commercial companies and are interacting with the government on these systems. Can you talk a little bit about how, has there been changes in the way you've had those relationships with on the government side, or how have they helped each other, I guess?
I've seen a lot of changes over the last 10 years, you know, the commercial-public partnerships, and I think there's a lot more risk on industry today than I've seen in the past, and a lot of the contracts that we're entering into now are firm fixed price with very aggressive schedules. If you look at the Gateway schedule, Maxar agreed to deliver a 70-kilowatt system in 3 years, and that includes, you know, the launch costs and everything else for a pretty low price. So there's a lot of pressures on cost, a lot of pressures on schedule. There's a lot more, you know, required of industry to participate through investments in kind or actual investments, whether they be through IR&D or whatever, but you know, sharing a cost-sharing kind of a relationship. So I think that I see industry experiencing a lot more risk over my time in the business than we have 10, 15 years ago.
Yeah, and I'd say we've seen, I'm trying to think of an easy way to say it, a lot of green light schedules where people in the past would have said, what's an attainable schedule and what does a fantasy land look like? And you know, we have those typical conversations, and now it's just we're baselining green light, and everyone is more. Development seems to be tossed by the wayside recently, and it's more we're hoping that what we initially picked as the basis for our technology is the correct one, and we are flying with that. So it's a speed up. So from my perspective, being relatively new to the space industry, it's probably healthy because people will start to realize that. Not every T has to be crossed, not every I has to be completely dotted by 400 people before it can actually go up in space. And I think that to some of the points that have been made about the low-cost LEO industry is they're right now proving that. Because we noticed there's a drastic difference between working with some government customers and sometimes people in a garage, and the levels of risk appetite that they have, and then their expectations from us. So I think it's starting to really broaden the scope to complement your point.
Really interesting discussion from what we had earlier today about how you make the transition and on what programs you make the transition from the large and the low risk types of programs that are high dollar value to even high dollar value ones, but you have a different either schedule or cost profile that you've got to respond to. So I think it's a challenge for the community overall. Jim, do you have any questions?
Yeah, sure. So we've got some questions from the conference IO thing. So the first one, we've heard discussions today on the importance for innovation. So where do you see the next innovations specifically for power?
Okay, so from the radioisotope and from fission power, I think you're going to see a increased emphasis on dynamic power systems with moving parts, which allow for much higher efficiencies for a given heat input, much higher electrical output. That's going to require some innovation as well in terms of lifetime prediction, and we're already working on some of that where we're trying to understand the wear-out mechanisms and learning how to model them and start to predict life. But I think you're going to see an emphasis on efficiencies, and obviously there's a mass reduction with that. And as I said, I think dynamic power is really going to revolutionize from NASA's and my program standpoint.
Anybody else want to answer?
I can add a couple things. I think I'm seeing more focus coming on nuclear power systems, whether it be FSP, fission surface power, or nuclear thermal propulsion, as the desire to explore the deeper parts of the solar system. That technology is very critical. And you go to places like Mars where the dust storms are overrated. I guess they're not as bad as we read or hear about, but they still have an impact on solar power. So I think I got to attend the kilopower test last year at the Nevada Nuclear Test Site, and that was one kilowatt. You need to get to probably 40 kilowatts. So I see a focus in that area coming.
One thing that I think we've highlighted on some of our technology roadmaps is the advent of GaN transistors, and to couple with that, the increasing frequency at which you drive those systems. It's a holistic look. The faster you can drive your conversion system, the smaller your magnetics and the higher your specific power gets. So I think from our standpoint, it's really starting to take the next jump in transistor technology.
Excellent. All right. And I like this one. This is a good one. So for Greg and Larry, what can John and Tracy do better to help you advance power technologies for future missions, both crewed and uncrewed?
Well, I'd like John to be nicer to me for starters. But no, I think one of the things John and I have talked about in the past is actually the contracts coming at every 5-10 years. I think we're seeing a little more activity now, which is great. But in the past, you have a problem in retaining your skills. Your engineering team, they don't sit around and wait for the next contract to come. They get redeployed. We've got a number of folks at our facility that I'm trying to hang on to that are now being redeployed to the RS-25 for SLS. And so you get some people, they work on your project, they're very good, you depend on them, and then they're waiting for the next contract. So I think that's an area that would be very helpful for my business. Greg?
Take a chance. I mean, from an innovation standpoint, there are new things being created every day, and I think accepting a larger risk profile for some of the big vehicles that are coming. Yeah, it's easy for me to say, and it's hard to actually follow through on, but eventually I think we might need to get there.
Do we have any other live questions in the room here?
No? Okay. Well, I've got a couple more that have been submitted. So this one, and I might botch this up a little bit because it's not language that I necessarily speak. There are strict government laws about the protection of HEU power systems, and with kilopower using HEU, is the Space Force going to protect it on the moon?
I really don't have any. See, I can't operate anything. I really don't have any insight to that. I mean, I don't think there's been a lot of discussion regarding deployed systems, you know, once things have been deployed. So that's probably an area that needs to be focused, you know, and probably have some more discussion as those programs evolve.
I want to say just one thing. You know, with any kind of nuclear flight, you have to really go all the way up to the president to get authorization to proceed because of the safety aspect. When we first, you know, launched the MSL mission, the Mars Science Lab mission, I was interviewed in my office in Los Angeles by the local news station, and they kept hitting me with questions about the safety of the MMRTG. So, and we were warned when we went out to see the launch to be prepared for protesters. So I just think that, you know, at the highest levels of our administration, there'll be careful scrutiny in terms of the safety, and the NRC will be involved. So I can't comment on the Space Council because it's so new, but I would think similar kind of, you know, safety will be implemented.
And I think just time for one more here. So how much does NASA's level of demand for advanced power technology drive your innovation for other commercial markets?
That's a very good question. I think as we go on, I'll use Stirling as an example of dynamic power system. I think NASA's been involved with the development of Stirling for power, and there's a synergy there with terrestrial systems. There's a lot of terrestrial solar-based Stirling systems, and there's been a lot of interaction between the commercial market and NASA with regard to these systems because the Stirling engines give us an opportunity to have a very high efficiency power conversion system. By the same token, when you can run a Stirling engine either way. You can either run it as a heat engine or as a cooler, all right? And so it just depends on what end you put the heat into, right? And so I think there's been a lot of synergy there, and I think we've helped each other. I think the developments that NASA goes to with those engines to increase the reliability, to increase the lifetime, then translate into the commercial market. You know, we obviously need to have very high reliability. And to your comment earlier, take a chance. We're certainly willing to put forward these systems. It's one thing to develop the system. It's another thing for the community, and this is the other thing that has to happen. It's another thing for the community to embrace that technology and run with it, because you know, in the case of a dynamic power system where you're talking about you've got moving parts and you can't touch it and you can't change the oil or do anything for it for 10, 15, 20 years, obviously the reliability of that has to be well established. And so the mission community can be somewhat reluctant to take that on because they don't necessarily want to hang their hat or their mission on a device like that. So.
I can comment too. Another area in addition to the Stirling, is battery technology. So for the Dream Chaser, we're building batteries, lithium-ion batteries, the 18650 Panasonic type cell, similar to the cells that are used for the Tesla. But the amount of safety that we're building into that battery is beyond anything that I've seen in years. And I think that's helped us with taking that, what we're learning on those batteries, where we have an interstitial material between each cell to prevent thermal runaway. We have fusible links on each cell. You've got a tremendously detailed, intricate battery management system monitoring cell temperatures and voltages. And so all that we're learning can be leveraged into industry. And I've talked to the Navy. The Navy's really reluctant right now with lithium-ion batteries because of the incident with the Navy SEALs a number of years ago. But I think in time, the battery technology is evolving at such a tremendous pace. I listened to a professor at Stanford recently talk about battery technology where you'll be able to charge a battery in these electric cars in 5 minutes, 10 minutes. That revolutionizes industry completely and opens up a lot of doors. So that's my thought on that.
I would just like to close. I don't know how many of you watched the National Geographic Mars series, but the episode where they have the power outage and shortage, actually I thought was quite insightful in terms of what happens when you're stranded on Mars or some other location, and you do have power failures or outages or shortages, and what it does to all the other systems. So I thought that was quite powerful. I'd like to thank John and Tracy and Larry and Greg and all of you for participating in our panel today.
Thank you.